In this video we'll discuss transformations. Transformation is the change in the position, shape, and or size of a figure. We'll be discussing the pre-image, which is the original figure, and the image, which is the transformation of that figure. When we label, the pre-image will get the original letters based on the vertices, whereas the image will get a tick mark, which we say is prime. So if we had the letters A, B, C in the pre-image, the image would be A prime, B prime, C prime. Our first transformation is the translation. This shifts every point on the plane a specific distance and direction. This can either be given to us by units moved vertically and horizontally or as a vector, telling us distance and direction. So here's our first example where it's telling us to move triangle ABC 3 units up and 2 units to the left. While we may be translating ABC, we are translating the entire plane, but we represent it through the shift of triangle ABC. So all 3 of those vertices we show up 3 and to the left 2, and we can plot our new points A prime, B prime, and C prime. And we can say there is our translated triangle. We also can be given a vector, in this case PM, and we can then connect that vector to each of those points to help us locate where A prime, B prime, and C prime should be, and plot those 3 points then. And if you think about it though, the vector, all it's doing, if we follow the arrow, it goes up 1 and to the right 5. So it is giving us this movement, it's just giving it through the visual of the vector. Within translations, we can have translation symmetry, which is when a design or pattern can be infinitely translated on the plane. While we view only a portion of the design, we do want to test both looking vertically and horizontally to make sure that pattern will always look the same. So here's an example of a pattern. If I shift it horizontally, I would see that the pattern continues to go. And if I shift it vertically and I line up, I would see that the pattern will continue if I went downward. So it goes both horizontally and vertically, therefore this would be a pattern with translation symmetry. Now with the reflection, we're creating the mirror image the exact same distance from the line of reflection. So the plane is actually being reflected on both sides, even though we are looking primarily at a figure. So first we need to determine our line of reflection and then move each point the same distance away from that line on the opposite side. And remember, distance is a perpendicular distance from that line of reflection. So say that I have MNQP across the x-axis. So there's my line of reflection. Now I'm looking at each of those vertices because that's the easiest thing to focus on to help me figure out how do I reflect. So I see that point M is 1 unit above, so M prime would be 1 unit below. I see that N is 2 units above, so N prime would be 2 units below. Q is 3 units above, so Q prime would be 3 units below. And then P is 4 units above, so P prime would be 4 units below. And then I can connect my 4 points, and I have my reflected version of MNQP. Now with reflection, we can also have symmetry. And this is when we can take a line in a plane, and we draw it through that figure, it can make the mirror image on both sides. There can be 0 lines of symmetry, but there can be many lines of symmetry as well, depending on the figure. What we want to do is try to draw it so that we can figure out how can we match up the shape perfectly. So if we look at this first one, if we drew a vertical line and then took this right hand side and folded it across the line, it would not match up perfectly with the left hand side. However, if we drew in the middle horizontally and then folded up, we'd see that they do fold perfectly on one another. So we'd say there's one line of symmetry, and it'd be this horizontal line. Now if I look at my double arrow, if I drew the vertical line, I could then take the left side and fold it on the right side and it'd match perfectly. But I want to test other types of lines too. So if I take and go horizontally, I could take the bottom, fold it up, and it would fold on top as well. Now when I get to my third shape, and so this would have 2 lines of symmetry. When I get to my third shape, if I draw that horizontal line and take and fold the top down, well, the curves don't match up. You can see how things just are not matching. So that's not a line. And if I drew one in the middle vertically and tried to fold over, I'd see, well, this doesn't match up either. So this has no line of symmetry. So there's no reflection symmetry in this image. Now we can also combine, create a combination of transformations. One of those is the glide reflection, where we first reflect along a line and then we translate along that line of reflection. And this will create reflection symmetry as well, where I can take that image that's been created by the glide reflection, it will continue infinitely. So if I want to test it, I just want to take my design and I can translate it to see that it does continue. So let's create a glide reflection, and then we can test it for symmetry. So here's my image. I reflect it first, and then I translate it a certain distance. Now I reflect it back and translate it that same distance. And I keep going back and forth, reflecting and shifting, reflecting and shifting. Then what I can do is I could then say, okay, let me try to test this. If I take all those images, if I reflect them across the line, and then I shift them, if it's a glide reflection symmetry, everything will match up. And I can see that is what occurs, hence because I created it. Another transformation we'll deal with is the rotation. And rotation turns all points in a plane a fixed angle about a fixed point. So we need to know the center of rotation and the angle at which we want to rotate. Also, we need to know the distance of each point from the center, so that as we rotate the points, we maintain that given distance. So say you want to rotate the following triangle, TUV, 90 degrees counterclockwise. So we do pay attention to whether it's clockwise or counterclockwise. When I do that, I could use, since it's 90 degrees, I want to keep that perfect angle, that I could use a piece of paper or I could use rulers, and that will help me know where to put that new point for T. And I can do the same thing for V, and then the same thing for U. And what I should recognize is that when I rotate a 90-degree angle, look at what happens to my ordered pairs. Each of the ordered pairs have flipped around, and then I just have to pay attention to what quadrant I'm in as to whether the X or the Y needs to change to a negative or a positive. But that's one of the neat things about the 90-degree rotation in the coordinate plane. Now rotation can have symmetry as well, and this is where if we know our center and as we rotate it a specific angle measure, it will always be consistent with the original shape. So a 60-degree rotational symmetry would look like the same shape every time I rotate it 60 degrees. Let's create a 90-degree rotation. So if I took this image and rotated 90 degrees about A and it kept going around, then I could take that image and I could actually rotate it 90 degrees, and even though I've got these colors to show the differences, I'm matching up every single time with my image because it has that 90-degree rotational symmetry. Now, our three transformations we just discussed, translations, rotations, and reflections, they don't change the shape, only the position and location. So these are called isometric transformations. So if I took this arrow, I could translate it, I can rotate it, and then I can translate it again. It's still congruent to my original arrow. That's what makes it isometric. Now our final transformation we'll discuss is dilations. This is a non-rigid transformation, so it's not isometric because the images created are similar to the pre-image. It starts with a center, which we'll call C in this case, and the corresponding points of the pre-image and image will fall on the same line to C, and they'll have the same ratio. So let's look at an example to help explain what this means. If I look, I'm going to use my center as point A down here, and I'm going to create a dilation that's a scale factor of 2, so it's going to be twice as large. This is an enlargement versus a reduction, which would be shrinking. So every side is going to be twice that of my current quadrilateral. So if I start with thinking about, well, how can I create that? I can see that point E is 3 units from A. that means if I'm doing a scale factor of 2, that E prime would have to be twice as far away, so it'd have to be 6 units from point A. And you can see E and E prime fall in the same line. Same thing with D. It's 3 units, so that means that D prime has to be 6 units. And again, they fall in the same line connected to A. Now I'd want to do the same thing for B, but that's a hard measurement to do. So I can use my scale factor to help me. And I can recognize that BE should have a scale factor of 2 from E prime to B prime. So if this is 2 units, then I should know that E prime to B prime should be 4 units. And if then I connect my line, again, they fall in the same line, and I could use the distance formula to find this exact measurement and see that it is a 2-to-1 ratio. Same thing with CA to C. That's a hard measurement to figure out what's double, but I can use the scale factor and go D to C should be D prime to C prime. I should have that ratio of 2-to-1. And again, if I connect the lines, I see they fall in the same line, and I could use distance formula if I truly wanted to check and make sure it's exactly a 2-to-1 ratio. So here is my quadrilateral that is a scale factor of 2 for B prime, C prime, D prime, E prime.